A very warm good morning to one and all. I welcome you all to the day 3 of this short-term course STEM 2023. Today's session will be taken by Professor S. Gopalakrishna from NIT Rourkela on the topic Direct Power Control of Active Front-End Rectifier. Professor S. Gopalakrishna received a bachelor degree in Electrical and Electronics Engineering from JNTU College of Engineering, Kakinada, India, a master's degree in Power System from the National Institute of Technology, Jamshedpur, India, and PhD degree from the Department of Electrical Engineering, IIT Madras, India. He joined the Department of Electrical Engineering, National Institute of Technology, Rourkela, India in 2011, where he is working as an associate professor. His current research interests include power quality, electrical drives, measurement, and instrumentation. 3 PhD students graduated under him, and he published in renowned journals like IEEE Sensors, IET Power Electronics, and IEEE Transaction on Vehicular Technology. Now I welcome Professor S. Gopalakrishna sir to deliver his lecture. Now it is over to you, sir.
Okay, good morning everybody. So today on behalf of this STEM 2023, I'm going to deliver a talk on direct power control of three-phase active front-end rectifiers. So this is a control technique that is used for conversion of DC to AC to DC. Okay, so let us see what is this one. So why this work is important? So what is the need for this this research on this one? So need for AC to DC conversion. So it is required in industries if you see. So electric drives are one of the major components of industries. We cannot imagine an industry without electric drives. So electric drives are very important. So for electric drives you require a large amount of power which is DC. Okay. So AC to DC conversion is essential, very much essential in here. And EV charging systems, we know that right now many of the vehicles are going for electric vehicles. So there we require a DC power supply to charge the vehicles. So where we should have a AC to DC conversion. And lighting applications, you can see LED. So if you see whatever LED bulbs we are using at our households, so that will be having inbuilt AC to DC conversion for each bulb. But if you have a combination of you can say complete lightning system is converted by using AC to DC, then it will be very good. That means you can save a lot of money and energy also. So here there are a lot of applications. So just few of the applications I have showed. And you can see a classical technique which is used for AC to DC conversion. So there we can see that a direct bridge rectifier is used, a simple direct bridge rectifier, and between the direct bridge rectifier and the AC source. So you are having AC source. It may be a grid, or it may be another generator may be used. So here you can see EA, EB, EC. These three are the voltages that are represented by for the AC source, and in between you are having some line inductance is there. So with this, if you see the AC to DC conversion, so this is the capacitor that is kept to filter out the voltage fluctuations, and because it is DC load, so it is simply represented by a resistance. Okay. So now if you see the current and voltage, the voltage of the a single phase. Suppose if you take a single phase, so you can see the voltage is a sinusoidal one, and the current. So if you take the current is non-sinusoidal, and it is not having unity power factor. Okay. So first of all, why this non-sinusoidal current is coming? That is because of the rectification process itself. Whenever there is a power electronic device that is involved, so definitely non-sinusoidal currents will be present. So here, because of the presence of diode, you'll be having non-sinusoidal currents, and because of the inductance, you see, because of the inductance, the current is shifted by some angle, and that is it is not in line. Okay. So this is the major disadvantage of this conversion. Okay. So what are the problems? So what are the problems that will come if you use the conventional technique? So then what are the problems are the disadvantages and advantages are given here. So advantage is, suppose if you use diode bridge rectifier, it is very simple. There is no need to control, it is uncontrolled. So it is very simple and it is cheap. So you are having cheap and simple. But there are disadvantages. So what are the disadvantages? It introduces source current harmonics. Because the source current is not sinusoidal in nature, it heats the source and transmission system, source utilization and efficiency are decreased. And the next one is the non-unity power factor of the source side. So because of the non-unity of power factor on the source side, the source has to supply the reactive power. Okay, so this is, we know, because reactive power compensation is a major issue. So this is the disadvantage of this one. So now what we can do for this one? So if you what is the with that, with latest techniques, how we can avoid this one? So here what we can do is, instead of diode bridge rectifier, if I replace all the diode bridge rectifier with switching devices, okay. So instead of diode bridge rectifiers, we are going for IGBTs. Here you can see IGBTs or MOSFETs or whatever it is. So we can go for these things. And now if you go like this, then what will happen? So if you are able to switch the devices in a proper way, okay, using a proper algorithm, if you are able to switch the devices, then you can see that the voltage is same as previous, but the current, if you see, the current waveform is improved. Improved means it is coming almost in phase with the voltage, and you can see that the harmonics that are present, there are still harmonics are there, but the harmonics that are present are higher order harmonics, which can be filtered out by using a passive filter. Okay, so this is a technique by which we can improve the quality of the power, or you can say the current quality, by using this, switching these devices in a proper way. Okay, so now this work, whatever I am going to tell this in this talk, is how to switch on these devices such that you will get this shape. Okay, so that is the idea of this talk. So now we have to start from the basics to understand this technique. So here, let us assume, so it is see that this work is having so much of advanced things are also there. That means they are going for an unbalanced supply and unbalanced supply with harmonics and all those things, but we are going for the basic one. So that is, we are assuming that the supply is a balanced one, that EA, EB, EC is grid voltages that are balanced. Okay, so so assumption here is balanced grid voltages with constant frequencies assumed. Okay, and then here you can see that whenever the supply is balanced, it is EA, EB, EC. If you convert this one to alpha beta axis, that means you can see that this, when you convert this, when you transform this one to alpha beta axis, so you will be getting a vector, a space vector. Okay, so if you have studied about the space vector transformations, so then you can see that the voltages EA, EB, EC can be represented by a space vector which is rotating in space. Okay, so how this one? So you are having you can take three axes: A axis, B axis, C axis. So if you see this vector, this E, the projection of E on A is going to give EA. The projection of E on B is going to give EB, and the projection of AE on C is going to give EC, something like that. Okay. So now if you use the transformation is, instead of having three axes A, B, C, if you can take two axes alpha, beta. So if you take alpha, beta, so when you are taking this transformation matrix, here you can see FA, FB, FC. Okay, so these are in ABC, and there's a transformation matrix, and you can convert into alpha, beta. And there is, whenever you are having transformation, so there should be an inverse transformation also. So what is the inverse transformation? Inverse transformation is represented by this one. Okay, so here So this is about this slide shows about the grid voltages. So now if you see what is on the converter side. Okay, converter side, suppose if you switch this converter in a particular way, how this is behaving. Okay, so suppose here we have to assume that the voltage across the VDC is maintained constant. Okay, so how it is maintained constant? That is by using a PA controller, we will be able to maintain that voltage constant. So here VDC is maintained constant. So here now selecting S converter side voltage gives the discrete voltage vectors on the converter side. That means here whatever you are getting E, so this is from the grid side. So this is a continuous vector. That means it rotates continuously. But whereas if you take the voltages that are produced by the converter, so the converter will not cannot produce a continuous voltages. It can produce only discrete voltages. So here, how the converter will produce? So suppose if you select SA, the top switch, and SB dash, SC dash. So it is called 100. Okay, if you select 100, so this converter will give you a voltage at this point. So that voltage will be like this. It is along the alpha axis. Okay, and if you select a different combination, that is if you select a different combination like this. So here I have selected, if you select a combination like this 110. So 110 will give you a vector which is like this, a 60 degrees shifted vector. Okay, so so one vector is here and another vector is here. Okay, so the voltage that is produced at the converter side is having a discrete levels. Either it can produce here or here, and in between it cannot produce anything. Okay, so similarly, if you select different combinations, so you will be getting different vectors like this: V1, V2, V3, V4, V5, V6. So different combination of these switches will give you different vectors like this. So now we have only one thing, that is we have a grid voltage which is continuously varying. That means this vector is continuously rotating like this, and these voltages are with us. So which are discrete in nature. We cannot have a continuous variation here. Okay. Now we are having a choice, because we can switch on these switches as we like. That means we can select these vectors at discrete points. And suppose if you select all three vectors, all three vectors as ones, so then, or all three as zeros, so then you will be getting a zero vector, that is here. Okay, so this can be represented by an equation, that is Vk. Vk can be represented by equation 2 by 3 VDC. That means 2 by 3. We can derive this equation. Actually, it is not difficult to derive. It is 2 by 3 VDC. The voltage magnitude, and e to the power of j k minus 1 into pi by 3. So this is the general equation for the converter voltage. Okay, so these vectors are called active vectors, and the vectors which are coming as a zero, that is having which is having neither magnitude nor angle, so that is called zero vectors. So now we can select 7 types of vectors, 6 active vectors, and zero vectors are 2, but they will be giving the same results. Okay, so 1. Okay, so 7 different types of vectors. Now see, for this classical method of direct power control, suppose if you take the classical method of direct power control, so the method is using table based. It is table based direct power control. Okay, so when in table based direct power control, if you take table based DTC or DPC or whatever it is, so there will be table which consists of sectors. Okay, so where the total space, if you see the total space here, the total space is divided into number of sectors. So the total space is 360 degrees. 360 degrees is divided into sectors. So here you can see the sector 1, sector 2, sector 3 like this. So in different literature, they have taken in different ways. Okay, some people are starting in an anti-clockwise direction. So this is a simple way of taking like this, right? And so now if you see the instantaneous complex power, so it is generally if you see the power, the apparent power or complex power, that is given by complex complex power is given by capital S, which is equal to capital P plus capital J, capital P plus capital Q. Okay, so here it is the instantaneous complex power. Okay, so that means this P is instantaneous quantity and Q is also instantaneous quantity. Okay, so that is given by 1.5 into instantaneous currents in star, instantaneous current star into E. Okay, so here you have to understand that this I, this is also vector. Okay, instantaneous current, but it is vector. Okay, this is a space vector and this is a space vector. So here you are having instantaneous current I. So this is a space vector and this is a space vector. So here the independent, if you see this this diagram, you can see that it is having converter vectors, sectors, and E and currents. So if you see this one, the E, whatever E is, it is there, that is not in our hands. It is completely dependent upon the grid. Okay, how the grid voltages are generated, it goes like that. Okay, continuously. So what is in our hand, we can select V. Okay, the V1, V2, V3, V3. So these things can be selected. Okay, suppose if you select, so out of these active vectors, suppose if you select V2. Okay, suppose if you select V2 here. Okay, so here the voltage is E. At this point voltage is E. At this point the voltage is V2. Okay, so it is coming here. So if you see this, the voltage drop across this one, across R and L combination. If you see the voltage drop will be like this. If you see the connect, if you connect this one, it will connect from here to here. Okay, the same thing, the same drop is drawn here. Okay, it is drawn here. Okay, so now you can see that R and L, if you take R and L, this L will be negligible. Okay, it is very less amount of value will be there, and L is dominating. So the current will be lagging the voltage by almost 90 degrees. That we already know. So here, because this is a drop, the current will be something like this. It's the magnitude of the current will be like this. So by selecting the current, by selecting the voltage, we are able to select the current. Okay, so that means suppose if you select V2, it is current is coming like this, and if you are selecting V1, the current will be coming in some other way. Okay, so out of this P plus JQ, this E is not in our hands. It is decided by the grid voltage, but I is in our hands. Okay, so we can do something about that one. So that is where we are able to control this one. So now if you solve this equation, see here whatever equation is there, P plus JQ. So that equation we have kept instead of taking S is equal to P plus JQ, if you take the rate of change of complex power, the rate of change, so that will give you P dot and Q dot, where P dot indicate the rate of change of instantaneous active power and Q dot indicates the rate of change of instantaneous reactive power. So if you solve that equations, and then you will be getting the equations like this. See here the equations are not consisting of current. Instead of current, the current is expressed in terms of UDC, L, and this K and these parameters. Okay, so what is K here? K is nothing but the switching vector, the switching vector number. So here, suppose if you select 2, then K is equal to 2. Okay, so here UDC is nothing but the voltage across the battery, the capacitor. Okay, so this is in this way we can see that the equation is depending upon, here you can see the only depending variables is, so it is K, and I think only this is depending upon K only. So if you know the K, because UDC is constant, and if you know about K, this omega t is depending upon E, and the magnitude of E is always constant almost, because the grid voltage is almost constant. So it depending upon only this one. And suppose if you take Q, it is also depending upon K, and so depends upon omega P. Okay, P is the power requirement of the load. Generally, suppose if you take a constant load, constant power load, so then that P will be constant. Okay, so it depends upon this thing, these terms. Okay, so now if you select, this is the case when you select the active vectors. Suppose if you select the zero vectors, so then you are having this P dot and Q dot as like this. Okay, that means these terms will be eliminated. Okay, and only this like this. So this is how the rate of change of active power and reactive powers are there. So now what I will do is, first of all we have to, because this is table based direct power control, first we have to form the table. So how to form the table? So first of all what you have to do, we have to draw the graph for this one. Okay, so just you can see that if you keep K is equal to a constant, let us take K is equal to here, because we have taken 2, K is equal to, suppose if you take K is equal to and change this omega t from 0 to 360 degrees. So then you know the values of these things. So these things are given in the paper. Okay, whatever reference we have followed, that in the paper these things are given. All these parameters are given for us. So these things are known. So if you change this omega t from 0 to 360 degrees, you will be getting a graph like this. Okay, so you can see V2, for V2 a green line is coming here, a dotted line, green line is coming here. Okay, so you can get a graph like this from 0 to 360 degrees. So similarly for Q you can plot a graph here. So this will come like this, green line is coming here like this. Okay, so now after plotting a graph, and similarly we have to plot a graph for the zero vectors also. So if you plot a zero vectors graph, you can see that this is a constant. It doesn't depend upon the switching. Okay, so it is a constant here. So here this is a constant, this is a constant. So you can see that the constant is represented by a black line here. This is a constant, and here line this one. Okay, now how to form the table. So how to form the table, let us see. So this is how we have to form the table. So let us take one sector. So first sector 0 to 30 degrees. So this one, this point. So I am keeping a rectangle box here. So the first sector is taken here. So here in the first sector, it is S1. Okay, if you take S1 here, then what are the things that we have to see? That means suppose if you want the active power to increase, the active power should increase and reactive power should increase. Okay, so that is 1 1. Active power should decrease and reactive power should decrease, 0 0. Okay, so these are the different combinations. Active power should decrease and reactive power should increase, and here active power should increase and reactive power should decrease. So these are the 4 combinations. Okay, so just we have to see how which, by selecting which combination of vector will be getting these different combinations. Okay, so here suppose if you take the first case, so that is 0 0. I want both active power and reactive power to decrease. Okay, active power should decrease and reactive power should also decrease. So you can see that the red line here is below 0. The red line is below 0, and here the red line is below 0. So this is the only combination that exists for decrease of both active power and reactive power. There is no other combination. So here this red line and this red line. So the same thing is, that means only V1 is there for that. There is no other thing. Okay. So similarly, if you take the other thing, that is the second one, 0 1. Okay. So 0 1, active power should decrease and reactive power should increase. So here you can see that the literature has taken like this, that is here active power should decrease, but here it is negative is not existing, but nearer to 0 is existing. So that you can choose, and here it is this should increase. So this should increase. So you can see that the green is selected here. So that means V2 is selected. So this is V2. Okay. So similarly, if you take 1 0,
three generators are classified as area 1. This generator is classified as area 2. Okay.
Hello.
These three generators are classified
Sorry
as
to interrupt.
area 1.
Someone's mic
These
is on. Please
two
mute the mic.
generators, this generator is classified as area 2. Now, G1 and G2 are two generators, right? G1
Sorry.
and G2 are two generators in same plant. In same plant. G3 is the another generator in
okay, for the first two, okay, for the first two, you can see that only one combinations are available. But if you see the last two the combination, that is active power should increase and deactive power should decrease, there is more than one combination is available. Okay, so here in the literature what they did is, some people have selected V6. Suppose if you take V1, V2 is selected generally, there is no other choice. Some people have selected V6, some people have selected V5. Similarly, out of these three, some have selected 0 vectors, some have selected V3, V4, and different papers are there which are selecting different vectors for this one. Okay, but and they have given the final results that this is a improved table like that. Okay, so this we have made some better see, out of this V6 and V5, what we have done is, which is the best for the given load condition. Okay, so that how to choose. So that is the proposed work. Okay, so here this is a general representation of the, here I have represented as VK, V1, V2, V3 like this for the sector 1. But in general, suppose if you want to represent the table, entire table, so by using K you can represent. Okay, if you keep K is equal to 1, you'll be getting sector 1. K is equal to 2, if you'll be getting sector 3. So like this, it is general representation of the table. So how this is, the classical table is executed. So that means how this algorithm is executed. So here you can see our aim is to convert AC to DC, and with the condition that the power factor should be unity, and the next one is there should not be any harmonics. So these are the conditions. So here for that we can use three sensors, three voltage sensors. So which you will get EA, EB, EC. So this will give you the vector position where the voltage vector is. So EA, EB, EC are used for the voltage sensors, and current measurement is required. So E alpha, E beta, and I alpha, I beta. So by using this one, we can calculate what is P and what is Q, and we have to get the reference P. So the reference P can be obtained from the VDC. Okay, so that means here whatever voltage is there, so that voltage should be taken with a reference. The error is given to PA controller, and then from the PA controller we are getting the reference P, and this reference P is given to hysteresis controller, and then hysteresis controller output is nothing but a decision signal whether to increase Q or decrease Q, increase P or decrease P. So that is a decision signal, that is SP and SQ, and you are having the angle of this theta is the angle of this space vector E. Okay, so that is fed into this one. From this one, it will be giving in which sector it is. So that is theta n. Theta n indicates in which sector it is. Now here this continuous one is changed to discrete. So from this one, it is given to switching table, and then switching table will generate the switching pulses that will operate the IGBT, and then you will be getting the signal like this. Okay, so here you can see that voltage is coming, so voltage is sinusoidal and current is coming nearly sinusoidal. Okay, with improved power factor and improved decrease in harmonics. Okay, so here this is the classical method. Okay, and here you can see the with the change in load. Suppose if the load changes, suppose here if RL is there, if I am making it 2 RL, or if I am decreasing the resistance by 2 RL by 2, then what happens? There is a change in load. So how it is responding? So it is taking approximately 65 milliseconds to come to a steady state. Okay, with the change in load. So this is what we observed. So this is about the classical method. This is how classical method works. So now I am explaining about the proposed method of DPC. Um, so this work is published in IIT Power Electronics. So here what we have done is, so see whatever I told in the previous one. So here you can see this we have concentrated on this part. Okay. So when there are several combinations that exist, why to choose one? Okay, why to go for one? We can go for a proper decision at this point. Okay, so that is what the paper is about. So classical methods of DPC select the switching vectors based upon the sign of the instantaneous active and reactive power demand. That means whether it takes only two things only into consideration, whether we want to increase or decrease the reactive power, only sign. Okay, that means example, small increase in reactive power. Suppose one requirement is there where you require only small increase of active power and small increase of reactive power. Okay, then also it will select the same vector. Large increase of active power and large increase of reactive power, then also it will select the same vector. There is no distinction in the classical method. Okay, same selection in spite of multiple options. Okay, so control technique works better if vector selection considers the magnitude of instantaneous power. Okay, we should not consider only the what do you call increase or decrease. We have to see the how much increase and how much decrease, whether it is more or less. So the proposed method is based upon, so now here the proposed how you propose the method, it is based upon the average increase or decrease of instantaneous power in a sector. So we are taking the average. Okay, so how I will show you how we will take the average. So here we can see here in the classical method, in the whenever we are forming the table, we are seeing whether the active power is whether this active power is negative or positive. That thing only we are seeing, right? So instead of seeing only the whether it is negative or positive, if you take the average of this one, okay, so average of this one over this small interval of time, okay, so that will give you a better information. Suppose if you take the average of, suppose if you are having multiple options here, so this is positive, this is positive, this is positive, okay, all these are positive. So out of this all positive, suppose if you take average of this one and average of this one, okay, so this average will give you less amount of magnitude, and this average will give you large amount of magnitude. Okay, so by taking the averages, we will be able to know which is better. Okay, so here how to take the average? So the average is taken like this: the rate of change of instantaneous power in n sector with n minus 1 pi by 6 to n pi by 6 as limits. The average rate of change of active power is P dot average, so that is given like this, and reactive power is Q dot average. During this period can be written as, so P dot average is given as, so 1 by, the interval is pi by 6, so 1 by pi by 6, and 0 to, you are having n minus 1 pi by 6 to n pi by 6 P dot d omega t. Okay, so similarly Q dot average is given like this. Okay, so now the equation is solved like this. So if you solve the equation, then you are getting some expressions which are um, that is P dot average is equal to P naught minus this expression. So where XP is given by this expression. Okay. So these expressions will give you the average values. Okay. And we have considered the voltages and the inductance in the laboratory this way. That means EL is equal to 90 volts line to line, and L is equal to 24 millihenry. So in this way we have considered the parameters. So with these parameters, if you draw the graph, if you take the graph of the different vectors, so it will come like this. Okay. So for this, if you want to take the average, so if you want you have to take the average for this small interval against for this next small interval. Okay. So like this, you have to take the averages. Okay. So after taking the average, we have normalized. Okay. So how to normalize? The normalization is done by taking the maximum value. The maximum value is taken, that is divided. Okay. Dividing the average value by the maximum value will give you the normalized vectors. So you are getting uh, P dot n and Q dot n is given by like this one. Okay. So these are the quantized vectors. So after this quantization, so you'll be getting normalization. You'll be getting quantized and normalized vectors. So here, why it is called quantized? You are taking the average. That's why it's called quantized. So this you are having V1, V2, V3. These values are obtained. Okay. Now you can suppose if you take this table, you can see whether suppose if you take 97 V4. Okay. So V4 is increasing P and V5 is also increasing P. Okay. Now you can compare which is increasing more. Okay. This is increasing 97. This is increasing that 57. Okay. So the increase how much increase can be compared. So based upon the load requirement, if the load demands more active power, then you can go for V4. Otherwise, you can go for maybe V6 if the demand is less. So based upon that, we can select. Okay. So this is the contribution of this work. So converting the only that 1 and zeros to magnitudes where we can see the increase and decrease, right? So based upon this whatever values we obtain, so we have made a table which is in fuzzy terms. Okay, which take care of all the conditions. Okay, so here n indicates negative and x indicates that it is either high or low. Okay, it indicates both conditions, and similarly h indicates high, l indicates low. Okay, so that means if you want positive high, positive low, negative high, negative low. Okay, so these are the four things are there, and for four combinations. Okay, increase decrease, increase increase, decrease increase, and decrease decrease. So there are four combinations. So there are total 16 will come. Okay, so these are represented in terms of a table here like this. This is a falsified table. Okay, so just by seeing these values we can form this table. Okay, so after forming the table, so now we have to run the algorithm. So this is that's why we have given the name for this work as algorithm based direct power control. Okay, so instead of taking a table table based, but the classical methods are table based direct power control. Here it is algorithm based direct power control, where the table, it is similar to the table, but table is selected in such a way that it takes care of the magnitudes. Okay, so we will start from selecting taking the errors dp and dq. Okay, is the sector even, whether the sector is even or not, it will see. So if sector is even, then it is sector by 2, k is equal to sector by 2, and if sector is odd, then k is equal to sector plus 1 by 2. Okay. So here if is k dp, that means this is dp is less than 0 and dq is less than 0. That means if you want to decrease both dp and dq, okay, so then if we can see that there is only one combination, there is no other combination. Yes, if it is S, then select Vk. There is no other combination, only one vector exists, that is Vk. Okay. Similarly, then if it is no, then you can see that is dp less than 0 or and dq greater than 0. Okay, that means it is 0 1 combination. Here also there is only one vector we can select, that is Vk plus 1. So select Vk plus 1, it ends. There it ends. But if there is a combination, that is other two, that means previously I have shown the last two in the table, the last two combinations, that is 1 0 and 1 1. Okay, so for that we have to go for this part. Okay, so this part is we have to select, we have to go for either B. Okay, and here we are considering 50%, 50 as a value. If it is greater than 50, then we are taking it as high, and if it is less than 50, then we can take it as low. Okay, some threshold value should be taken for selecting whether it is high or low. Okay, so if the value of dp is after normalization it is more than 50, then it is considered as we have to select high. Okay, and if it is less than 50, we have to select low. And similarly in the negative side, it is in the positive side, but in the negative side also minus 50 is taken. Okay, so based upon that one we can select these vectors, other vectors. Okay, so you can see that the same algorithm is taken like this, and it will get, here you can see that all vectors are covered. That means whatever different combination of vectors, all vectors are covered, no vector is left out. Okay, so all vectors are covered in this algorithm. That means for different for different powers, different vectors will be used. And these are the results that are obtained from this one. So here you can see that uh, the power P, there is active power and reactive power, and current is nearly sinusoidal. Okay, and when there is a load change, the power P is increasing like this, um, and this is the how the current is increased, and this is Q. Q is almost remaining the same. It is not changing with the load, and the voltage across the capacitor is having slight dip. Okay, when there is a load change. And this is a comparison of classical DPC and the proposed DPC. So here you can see that uh, when there is a increase and decrease of power, so the active power ripple, you can see that is classical is 21.56 and 17.54, and here the reactive power is ripple is like this, and there is a considerable increase improvement you can observe here in the tables. Okay, and mainly the THD part is improved when compared to the classical one. Okay, and then tracking time. So how much time it is taking to respond. So that is also is considerably increased. So here here you can see the load is changed from 100 ohm to 50 ohm. The changes here are from 100 ohm to 50 ohm. Okay. So here what is the only disadvantage of this method is, so you can see instead of using a table we are going for an algorithm, so little bit complexity will be increased. So only that is a major disadvantage of this method. Otherwise it is good for using this one. Okay. Okay, that's all.
Now the now the session is open for discussion. So I request audience, if any query can put forward to sir.
Good morning, sir.
Yeah.
Sir, in fuzzy logic, on what basis we are taking the x value, sir? If it is high, we are taking the h, and low, it is low. But at what instant, even requirement based on how we are taking the x value?
No. Go to the slides.
Fuzzy, sir, fuzzy table.
1 minute. I'm just.
Yeah, this one, sir.
Yeah. So
X
here.
is high or low? At what? Yes.
See here, nx. Suppose let me explain one vector by other vector, then you'll be able to understand better. Okay.
Okay. Okay.
So here, if you see the first vector here, vector 1 v1. Okay, v1 is having -13 and -9. Okay. So here, that is the only combination that exists for this decrease of active power and decrease of reactive power. Okay. So here we have taken for negative high. You have, suppose if you take negative high and negative low. Okay. Similarly, for active power and negative high and negative low for reactive power. So there is nothing like low and high for low and high in this case, because there is only one vector, there is only one combination. There is -13 only exists. So there is, suppose if something else -40, some -50 exists, then we can go for that one. Okay. So here there is nothing like a negative high and negative low. Only one negative is there. Okay. So that is why we have given x here. So x means it is either low or high. Both the things are taken care. Okay. So this is a fuzzy term. Okay, it's not like fuzzy logic. It's a fuzzy term. Okay. It's a fuzzy terms only, not fuzzy logic. Okay. So then similarly, if you take the next case. Okay. In this case also, the second case, the vectors are 2 and 74, and there is no other combination is there. Okay, this first one is low and second one is high, so there is no other combination is there. So we are having nx and px. Okay, but if you take the other combinations, that is v3, v4, v5, v6, these things, so there you can see that you are having several choices there. Suppose if you take v3, okay, if you select v3, we can increase active power, we can increase the reactive power high. That means that means we can more the magnitude can be increased to high levels. Okay, both in the case of both active power and reactive power. Okay, so that is how we, because why we have taken pH here, you can just see here, that is v3. If you take, the values are above 50, 57 and 96, both are above 50. So we can take pH and pH. Okay. Similarly, if you take the case of V4, it is, one is 97, that is high pH, and V4 for Q, it is low, that is PL. Okay. So PL means positive low.
Positive.
So I think, did you understand this?
Yes, sir.
Whatever
Thanks. Yeah, thanks.
Okay.
I mean, the next slide, I think so. That is AND operator, sir. That one is algorithm.
Algorithm.
Next slide.
Yes, yes.
That is AND operator only, I think so. In comparison, is DP is less than 0, AND operator, that is AND operator, I think so.
AND operator.
And
Yes, yes.
operator. Yeah.
This one, if DP is less than 0 and
Yes, sir. Double ampersand is required, I think so.
That is actually in program we will be writing like that.
Okay.
Here it is an algorithm, no? So we can write even A and D and is also okay.
Okay. Okay, right, sir. Thank you, sir.
Okay. Any other questions?
Any more questions? So I request participants, if any question can mail to sir. Okay. So I want to express profound gratitude to Professor S. Gopalakrishna sir for such a wonderful and conceptual lecture on the control strategies of front-end rectifier based on direct power control method. Thank you very much, sir.
Yeah. Thank you.
And the next session will start at 11 a.m.